Welcome back to a deep dive. You sent over this really interesting technical paper and a bunch of fascinating images generated by the model it talks about. So today we're going to dive into that source material. Really, our mission here is to unpack the technical core of this model. The paper calls it BAGEL. We want to get under the hood, understand the architecture, the training, what it's, technically capable of.
Exactly. We're zoning in on those engineering decisions, the data strategies they used, and, well, the technical abilities Bagel ends up showing. Think of this as your shortcut to grasping the nuts and bolts from the paper itself.
All right, let's start at the top then. The paper kicks off discussing different ways, different philosophies really, for building models that handle both text and images. Can you break down the main technical camps they lay out?
Sure. The paper contrasts three main technical designs for these multimodal models. First up is what they call quantized autoregressive.
Okay.
This approach basically treats images like another stream of tokens, just like text. It predicts the next token, whether that's text or a visual token.
Seems straightforward enough.
It is relatively simple to build on existing LLM frameworks. But the paper notes, empirically, it tends to lag behind in visual generation quality. And generating images token by token can be pretty slow.
Right, the inference latency.
Exactly. Then there's the second type, external diffuser. This is where you take an LLM or maybe a VLM and you pair it with a totally separate diffusion model. They usually connect them with some adapter layers.
Okay, I've seen that approach.
Yeah, it can converge well in training, but it has this technical bottleneck problem. All that rich context from the language model, it gets squeezed down into just a few tokens before it hits the diffusion model.
So information loss potentially.
That's the argument. The paper suggests this compression can lose crucial details, especially when the task needs, long context reasoning.
Gotcha. And the third?
The third approach, and this is what Bagel is built on, is the integrated transformer. Here, the language model parts and the diffusion model parts are all unified within one single big transformer network.
One model doing everything.
Right. Now, this demands a lot more training compute up front, definitely. But the big technical payoff, it creates this bottleneck-free zone, visual info, text info. It can all interact really richly, right, through all the layers.
And the paper really pushes this integrated transformer idea, the Bagel approach, as the better path for scaling up these models.
That's their core argument, yeah. They believe this unified, bottleneck-free architecture, especially when you train it on massive amounts of data, particularly interleaved data, lets the model learn much richer multimodal stuff.
Interleaved meaning text and images mixed together in the training data.
Exactly. Text, image, sort of like a document. They think this is key for unlocking what they call emergent abilities.
Emergent abilities, meaning things that just sort of pop up at scale.
Kind of. Properties that really only show up when you scale the model and data way up. Things that maybe aren't captured well by our standard, simpler benchmarks. They see this integrated design having more potential for foundation models that need to do really sophisticated long-context multimodal reasoning.
Okay, let's get into the Bagel architecture itself then, the nuts and bolts. What's the foundation?
So the backbone, it's inherited from a decoder-only transformer architecture. Specifically, they initialize it from a pretty powerful LLM, Quen 2.5.
Okay, so starting with a strong language base.
Right. And it uses standard, proven components, things like RMS norm for normalization, SWGLU activation functions, rho-p for positional encoding, stuff you see in top language models. Oh, and one technical detail they add, which is apparently common for image or video generation stability, is QK norm. Helps keep training smooth.
Right. Now, how does it technically integrate the visual side? How does it see images?
For visual understanding, like taking an image as input, it uses a vision transformer, a VIT encoder.
The standard VIT approach.
Pretty much. Think of it as translating the image pixels into tokens the main transformer understands. They started with a specific pre-trained VIT, cyclic 2, initialized at a certain resolution. But to handle various image sizes, they use some technical tricks, like they interpolate the position embedding so it can handle images up to 980 by 980, and they integrate something called NIVIT.
NIVIT.
Yeah, it lets the model process images at their native aspect ratio, avoid squishing or stretching them.
That's clever.
Then there's just a small connector, a two-layer MLP network. Its technical job is basically just to align the dimensions, make sure the VIT tokens match the dimensions the main LLM expects.
Makes sense. And on the flip side, image generation. How does that work within the same transformer?
So for visual generation, it uses discrete visual tokenizers. Similar idea to text tokenization, but for image patches.
All right.
The transformer then just predicts and generate sequences of these visual tokens, like text generation but outputting image parts.
Yeah.
And there's a neat technical detail for interleaved generation, text, then image, then text.
Yeah.
When it's generating the stuff after an image, it attends back to the clean visual tokens of that finished image, not the noisy intermediate versions used during the diffusion process itself.
Okay. That's subtle, but probably important for consistency.
Seems likely.
Now, the paper mentioned they considered different transformer variants, dense, MoE, and landed on mixture of transformers, MoE. What is MoT technically in their setup? And why choose that?
Right, so they compared dense, standard mixture of experts, MoE, and their MoT. What's different about their MoT is quite chiding. Instead of having lots of small, specialized experts like a typical MoE,
Yeah.
they actually duplicate all the trainable parameters of the base LLM. So they create a full-size generation expert alongside the main model.
Wow. Okay, so two full models intertwined.
Essentially, yeah, sharing some components, but with duplicated parameter sets. The paper suggests this MoT design technically helps mitigate conflicts.
Conflicts between understanding and generation.
Exactly. Conflicts between, say, seeing an image and describing it versus taking text and creating an image. They found this MoT design kept performance strong across both kinds of tasks.
Okay, that's a significant architectural choice. Then there was this term, generalized causal attention. Sounds complicated. What's its function?
Yep, that part's fascinating. It's about how they technically manage the flow of information during generation, especially with mixed sequences, text, images, over time. They use something called PyTorch flex attention, partly for speed benefits.
Right.
The generalized causal bit means when the model generates a new token, it can only attend to tokens generated before it. That includes text tokens and visual tokens from previous parts of the sequence.
Standard causality, but across modality.
Pretty much. And technically, this structure is also set up to efficiently cache the key value pairs during inference.
The KV cache for faster decoding.
Exactly. Speeds things up, especially for long multimodal sequences. And importantly, only the KV pairs from the final clean generated images get stored in the cache. The intermediate noisy tokens are discarded once an image is done.
Efficient.
And one more trick. They use random dropout during inference.
Dropout during inference? Usually that's just for training.
Right. They randomly drop out text tokens, VIT tokens, or clean VAE tokens with certain probabilities. This is a technical way to enable classifier-free guidance.
Classifier-free guidance, giving more control over the output based on the prompt.
Basically, yeah. More control over style, fidelity, how strongly it adheres to the prompt without needing a separate classifier model.
Okay, got it. Now, training something this complex, it must be a huge undertaking. What's their technical strategy, a multi-stage approach?
Definitely multi-stage.
Yeah.
Very structured. It kicks off with an alignment phase.
Align.
Yeah, basically teaching the VIT encoder and the LLM to talk to each other. They freeze most of the model and just train that little MLP connector using image-text pairs.
Okay, getting the representations aligned.
Exactly. Then comes the big one, large-scale pre-training. This is on a massive, diverse mix of curated data. We can talk more about the data mix later.
Right.
After that, there's continued training. Here, they technically dial things up, increase the image resolution the model sees, and crucially, increase the proportion of that interleaved multimodal data in the training mix.
So leaning more into the complex mixed data later on.
Seems like it. And finally, there's a supervised fine-tuning stage, using high-quality instruction-following data pairs to really polish the model's abilities.
Makes sense. So about that data, what kinds of technical data sources are feeding this? You mentioned interleaved data being important.
Hugely important, according to the paper. They pull from diverse sources, but really emphasize interleaved multimodal data, especially from video and web documents.
Why video specifically?
While the paper argues video data is technically very rich. It captures real-world dynamics, time, space, how things move, object identity, consistency across frames, fine-grained details changing.
So it learns about physics and continuity.
Sort of, yeah. Stuff that's crucial for more advanced abilities like editing or manipulating images realistically. And web data gives it that broad general knowledge base needed for reasoning.
And they must filter this data heavily, right?
Oh, yeah. They mention a whole suite of technical filtering techniques, things like removing images based on URL substrings, like getting rid of UI elements, filtering by resolution, aspect ratio, using clarity operators for image quality, checking text density with OCR to avoid, say, scanned documents, using CLIP scores for image text relevance, even using other LLMs to process and trim long web documents.
A lot of pre-processing effort.
Definitely. Quality control is key at this scale.
Now, you showed me that image earlier, the car made of tiny cars. Was that an example of the kind of text-to-image data they train on? It seemed quite creative.
Yes, exactly. The source material lists that specific image, a car made of small cars, as an example from their pipeline for generating T2I training data.
So they generate some of their own training data.
They do. It's quite a technical process they describe. They start with intentionally ambiguous prompts or concepts. Then they use a powerful LLM Quinn 2.572B, prompted with examples, to expand these vague ideas into really detailed, descriptive prompts, like a chain of thought.
Okay.
Then that detailed prompt is fed into a different model, FLUX.1 dev, which is just focused on generation, to actually create the target image.
So they use one model to generate detailed prompts and another to generate the image from that prompt.
Right, and that creates a training triplet.
Mm-hmm.
The initial fuzzy query, the detailed reasoning or prompt, and the final target image. That triplet then feeds back into BAGEL's training.
That's a sophisticated way to generate high-quality, complex training pairs.
Seems very effective for pushing the model's capabilities.
Okay, let's talk about those capabilities, especially the emerging properties the paper highlights. That sounds intriguing. How do they technically define emergence here?
They frame emergence as a qualitative shift, a dramatic improvement in some ability that you couldn't just predict by smoothly extending the early training curves.
So not just getting gradually better, but sudden leaps.
Kind of like that, like hitting a phase transition where new skills suddenly unlock or become much stronger. They observe it technically by tracking performance on different benchmarks over the training checkpoints. You literally see performance jump at certain scale thresholds.
Fascinating. And what's the sequence? What abilities emerge first and which ones come later as they scale?
The pattern they describe is really interesting. Basic stuff comes first, understanding images, generating reasonably high-fidelity images. That appears relatively early in the training.
Okay, the fundamentals.
Right. Then, more complex things start to surface. Advanced editing, like intricate changes, and more flexible, free-form visual manipulation.
So going beyond just generating from a prompt.
Exactly. And finally, they see long context reasoning abilities really solidifying. And importantly, these long context skills start benefiting both understanding and generation tasks.
So the skills start combining.
That's the implication. It suggests these earlier, maybe more atomic skills, technically synergize into more complex compositional reasoning as training progresses and data complexity increases.
To measure this, they developed their own benchmark, Intelligent Bench. What's that specifically designed to test?
Right, Intelligent Bench. The authors created it specifically to probe these emerging capabilities, especially the ones involving complex multimodal reasoning.
Things not captured by standard tests?
That's their claim. They argue that existing public benchmarks, while valuable, don't fully stress test these higher-level reasoning abilities that emerge at scale.
Makes sense. But how does BAGEL actually stack up on the standard benchmarks we do have?
It does very well, according to the paper. They report strong technical performance across a whole range of common benchmarks. For understanding, things like MME, MMBench, MMMU, MathVista.
The usual suspects.
Yeah. And for generation, Genevol, WISE. At the 7 billion parameter size they focus on, BAGEL technically outperforms other existing unified models. And interestingly, it often matches or even beats models that are only specialized for understanding on those understanding benchmarks.
So the unified approach isn't necessarily sacrificing understanding performance.
Apparently not, at least in their results. They specifically call out big gains over models like Janus Pro on tough benchmarks like MMMU and MMVet. They attribute this in part back to that MOT architecture, technically reducing the task conflict we talked about.
Okay, let's make this more concrete with some of those images from the source material. Can you give us examples demonstrating these different capabilities?
Sure. The source had some great visuals. For the basic text-to-image and editing, there was that Audrey Hepburn series.
Right, you mentioned that.
Yeah, same subject, but prompts like wearing sunglasses, dancing in the rain, ice skating on Saturn's rings shows it can take a subject and modify it based on text.
Simple, direct T2I and editing.
Exactly. Then there were examples showing finer control, like images of a bracelet where the prompt changed the stone color or added a specific charm, like a tiny Eiffel Tower, shows technical object-level manipulation.
Okay, getting more specific, what about that intelligent editing category, the more complex reasoning stuff?
Right, this is where it gets interesting. These tasks need more than just following instructions. They require some world knowledge or multi-step thinking.
Like the bear example.
Precisely. The task asking to show what will likely happen when a man is near a bear and her cub. Generating a plausible image there requires the model to access knowledge about bear behavior, human interaction, danger.
And reason about a likely outcome.
Exactly. And the paper explicitly mentions that using chain of thought prompting technically boosts performance on these intelligent editing tasks.
How so?
Well, CoPT helps the model sort of think through the scenario, access its world knowledge, and generate more detailed internal guidance for the image generation step. The paper has figures illustrating this.
So the reasoning helps guide the pixels.
That's the idea. Other examples include showing the model a simple sketch of an octopus sculpture, and it generated a realistic photo of that sculpture. Understanding a design, then realizing it.
Design interpretation.
Yeah. Or the Shakespeare images changing his appearance, putting him in modern settings. Technical transformation based on understanding the prompt's context.
Okay, impressive range. But what about the limitations? What does the paper say is still technically hard, even for BAGEL?
They're quite open about the challenges. There are persistent failure cases, technically, that affect many models, BAGEL included.
Such as?
Things like accurately generating specific intellectual property, like famous cartoon characters. Complex text rendering within images is still really hard.
Like reading text on a sign in the generated image.
Exactly. Or generating really intricate or maybe just physically awkward human poses.
Hmm.
Or handling multiple instances simultaneously, like put 3 red apples and 2 blue bananas on the table correctly.
Spatial reasoning and counting issues.
Yeah. And tasks like precisely swapping object positions or deblurring an image effectively also remain technically challenging.
Interesting. Did they compare these hard cases to other models?
They did mention contrasting with GPT-4o, which they observed seemed more consistently successful on some of these specific difficult cases they tested.
So, room for improvement. How do they suggest BAGEL could get better at these things?
The usual suspects, mostly. Further scaling of data, especially data that actually contains text within images. Increasing the model capacity, so just making it bigger. And potentially using techniques like RLHF, reinforcement learning from human feedback, in post-training.
Right, the standard scaling paths.
Pretty much.
Okay, so pulling all this together from the source material, this deep dive into BAGEL really paints a clear technical mixture. We're looking at a unified integrated transformer, specifically using their mixture of transformers variant. It's trained intensely on huge amounts of diverse data, with a real emphasis on that interleaved multimodal data. And this technical approach leads to some pretty impressive capabilities, understanding, generation, complex editing, including these emergent properties that pop up at scale, which they're trying to measure with tools like Intelligent Bench.
That sums it up well. It's a strong case study showing how specific technical choices in architecture, like MOT, combined with a data scaling strategy focused on interleaved data, are really key drivers for unlocking new kinds of multimodal reasoning and these sometimes surprising emergent skills.
Yeah, it absolutely makes you stop and think, doesn't it? As these unified models keep getting bigger, keep training on ever more complex data, and these technical capabilities continue to emerge, sometimes unexpectedly, what entirely new forms of interaction or creativity, or maybe even, I don't know, scientific discovery could become technically possible, things we can barely even predict right now.
It's a fascinating technical frontier, absolutely. Lots to watch.
Definitely something to mull over. You can find links to the research papers we discussed today in the bio, as always. Until the next deep dive.